In this lecture, we're going to talk about power, energy flow, and plane waves. Now that we know what the plane wave solutions to Helmholtz equations look like, one of the most important things to understand is how we can quantify the amount of power that that wave is carrying. You're very familiar with the concepts of power from your circuit theory class, and when we remember that the relationships and the rules and the laws that we learn about lumped elements in circuit theory, when we remember that those are all related back to the electromagnetic fields that are supporting the currents and the voltages, we can understand that the fields are really being carried by the wave energy that's going on. So for example, in a transmission line, we can talk about power in terms of the voltage and current on the transmission line, but the voltage and current on that transmission line are supported by an electromagnetic wave, and the energy is bound up in the total fields. Two major learning objectives for this particular lecture. The first is to understand how to quantify power flow for time harmonic electromagnetic fields. And so you need to be able to use the Poynting vector. The Poynting vector is what we call the vector that quantifies the magnitude and the direction of power flow. So you need to be able to use it, apply it to solve power flow problems for plane wave propagation, waveguide propagation, antenna propagation later on in the course. And we want to understand about how Poynting's theorem and the Poynting vector are related to the concept of conservation of energy that you're all very familiar with from the other aspects of physics. And you need to understand, just comprehend the relationship between the two. When we have a wave solution to Maxwell's equation, what we're basically trying to do is carry power from one location to another. You could also say, well, I don't care so much about carrying power, I care more about carrying information, but those two are essentially the same thing. So if we want to be able to carry power or information from one place to another, we need to be able to quantify the power flow. Now, you're used to dealing with power in circuits, and you know that you can quantify the power in a particular circuit element by multiplying the voltage and the current, or more specifically the voltage and the complex conjugate of the current phasors. In wave propagation, we need to know more than just the magnitude of the power flow. We also need to know the direction that's associated with it, because if I have 1 watt per square centimeter flowing in this direction, that can be very different than 1 watt per square centimeter flowing in that direction, and I may care very much about direction as well. Excuse me. So instead of multiplying the electric field and the magnetic field, which in electromagnetic theory, we have vector quantities, so we have to use one of our vector multiplications, and we're going to use the cross product. You recall from your circuit theory, when you have transient currents and voltages, you get the power by multiplying them, and that gives you the instantaneous power dissipation or being provided by a particular circuit element. In electromagnetics, we'll take the Poynting vector, which is denoted here by this script P. And again, this is a time-dependent quantity. It's also a function of position, so I haven't explicitly written it, but it's an implicit function of position as well. So the power at any position at any time is given by the cross product of the electric field and the magnetic field. And when we go back to lecture 1 and the units, electric field has units of volts per meter, magnetic field has units of amps per meter, so I have a volt amp per meter squared. And of course, we recognize the volt amp as a watt per square centimeter, or watts per square meter. So this makes a lot of sense to us. It talks about power flow, and at any point in space, that field is carrying a certain number of watts per square centimeter. And if I have some aperture that the field is propagating through, I can quantify the total number of watts that make it through any aperture in my system. Poynting's major contribution to electromagnetic theory was Poynting's theorem. And you don't need to know this derivation, but I'd like to illustrate something. And this may look to you like a complicated mathematical formula, but before you worry too much about it, I want you to stop and take a look at it, and you know what each of these pieces are. On the left-hand side, what we've done is we've taken this Poynting vector, right? So this quantity here is just P, and I'm integrating the flow through a closed surface. So I have a surface S, okay, and I'm integrating the flow through it. If this flow is non-zero, that means that I have a net flow in or out of the volume. If the flow is equal to 0, then as much flow goes into the volume as leaves the volume. So that's what's on the left-hand side. It is the flow of this Poynting vector. Let's take a look at these terms on the right-hand side. This first term is the integral over the volume of the conductivity times the square of the electric field, sigma E squared. This is just Ohm's law, or more specifically Joule's law. This is just I squared R, or V squared over R, right? The power dissipated in loss inside the volume. And notice this shows up with a minus sign. So what that means is that if I'm dissipating some power inside this volume, that energy needs to come from someplace. Where's that energy coming from? Well, it's got to come from energy entering through that closed surface. The second term is the time derivative of 1/2 epsilon E squared. Right? Well, 1/2 epsilon E squared is just D times E. This is the electric energy density. This is the energy stored in a capacitor. Right? So this is the dissipation in a resistor. This is the energy stored in a capacitor, 1/2 CV squared. Right? And the third term is the magnetic energy, and this is equivalent to the energy stored in an inductor. It's 1/2 B times H, B dot product with H, and 1/2 mu times magnitude of H squared. And so this is the energy stored in an inductor. Right? So what that means is that if I have if I'm dissipating power inside a volume, that power has to come from someplace. It can come from energy flowing in, or it can come by reducing the amount of stored charge on a capacitor, or it can come from reducing the amount of stored energy in an inductor. If I add up these three terms, though, and it's non-zero, then that needs to be coming from the outside. Or if these three quantities, right, so if I am dissipating a certain amount of power, but I'm actually discharging more charge or discharging more current, and so these quantities here are such that they're large enough, then they can actually be the source of power that leaves the volume. Right? Because each of these quantities could, the time derivative of these quantities could be positive or negative. Right? So I want you to remember very much, you've got to relate these to the circuit elements that you're very used to working with. Right? So for a resistor, we know we have I squared R. And I squared R is just a macroscopic version of sigma E squared. For a capacitor, we have 1/2 CV squared, and that's equivalent to the microscopic version of 1/2 epsilon E squared. And for an inductor, we have 1/2 Li squared, which is the energy stored in the inductor. Okay? And so these macroscopic quantities down here that you're very used to working with, they're all related to these microscopic field quantities. In fact, they're completely equivalent. And this is just a general statement of conservation of energy. Okay? If I'm going to lose energy through loss, that energy needs to come from someplace. Now, in this class, we're mostly concerned with time harmonic fields. We've already talked about this, and really for the rest of class, we're going to be talking primarily about time harmonic fields. And so when our fields are time harmonic, then the Poynting vector P is going to take the form of P naught times cosine squared of omega t. And so this is going to be, it's going to oscillate between 0 and some large value, 0 and some large value, 0 and some large value. And we don't really care so much about this. We only care about the time average behavior. And this is analogous to circuit theory. In circuit theory, we have the average power being dissipated in an element is equal to 1/2 the real part of the voltage times the complex conjugate of the current phasor. And so by analogy, we can define the time average Poynting vector as 1/2. The 1/2 comes from the average value of the cosine squared. 1/2 the real part of the electric field crossed into the complex conjugate of the magnetic field phasor. Because remember, E and H are complex vector phasors. Right? So I take the complex conjugate of H, take this cross product, and that gives me the average power, with again my units being watts per square centimeter. So let's take a look at an example. If I have a uniform plane wave, it's polarized in the x direction and propagating in the z direction. So we know from the last lecture that here's my x polarization, here's my amplitude E naught, on a pen, not a rectangle, okay? And then my e to the minus j beta z tells me I'm propagating in the plus z direction. We know from Maxwell's equations that if my electric field is this, that my magnetic field is going to be in the y direction. Its amplitude will be E naught over eta, where eta is the wave impedance, and it's going to have the same propagation term, e to the minus j beta z. Okay? So when I do this operation, I've got the average power, it's 1/2 I'm going to take the real part. I've left out the real part here. Right, so I've got a real, whoops. So I'm taking the real part of this expression. The reason why it's left out is that this particular expression becomes real in the end, right? So I've got the electric field here, the magnetic field here. I can gather some terms. So on the previous, I had E naught times E naught star. Well, that's going to give me magnitude of E naught squared. I have a 1 over eta, so I have magnitude E naught squared over eta. I have e to the minus j beta z times e to the plus j beta z. They're combined here. And I have an x cross y. Well, x cross y is equal to z hat. E to the j beta z times e to the minus j beta z is equal to 1. And that tells me that my at-time average Poynting vector is 1/2 magnitude of the electric field squared over eta in the z direction. Right? And so this shows me I have this oscillating electromagnetic field, right, where I've got the electric field and the magnetic field. In this particular case, the electric field is the blue vector, the magnetic field is the red vector, which gives me the direct propagation in the z direction. So here's my electromagnetic field. My Poynting vector, P average, is in this direction. Notice that my fields are oscillating, but my time average Poynting vector remains constant. So that's the Poynting vector. There's a few questions in the tutorial. One of the things that's in the tutorial is looking at computing the Poynting vector, but specifically determining the time average power flow when multiple waves are present. So when we define this time average Poynting vector, it's the real part of E cross H star. If I have E1 plus E2 plus E3, I write them all down. Right? So I would have the real part of the sum of all my electric fields crossed into the sum of all my magnetic fields. And in the tutorial, you're going to see what happens when you have waves propagating in different directions and how those electric and magnetic fields interact in order to give you your time average Poynting vector.